Okay, guys, I'm going to try to re-record this. This was actually recorded previously, so I don't know if I'm going to say exactly the same thing as I said before. But the other version of the second lecture for AC, Introduction to AC, did not upload. There was an error, so I'm going to come back and try to attempt to re-record this. And I've changed the PowerPoints a little bit too. And I'll bring this out and I'll upload the newest version. Just to go back and review what we talked about, we talked about solid state, what solid state is and what it actually means. We looked at how we define and what actually produces DC or direct current, which is current that flows in one direct way. And of course, the biggest advantage of DC, it's very easily to electronically control. We looked at some of the devices that we're familiar with that generates a DC or direct current. Then we understand that solid state devices operate off of DC, and we look at a little bit about the power grid and other functions here. Then we got into an introduction of alternating current, and these are the terms we went over: cycle, frequency, period, alternation, RMS, peak, peak to peak, DC average of an alternation, and some of the components we had a brief introduction to are the AC voltage source, the inductor, the capacitor, and the transformer. This is what electronics, this is what the advantages of AC. It's less expensive to generate. It's extremely efficient to transmit. And we can easily change the level of the voltage with these devices called transformers. Of course, one of the big advantages and why AC motors dominate the motors, I guess, in residential and commercial use. There's all kind of DC motors out there. You can't say it dominates the field because every electric motor in your car is DC. So, probably DC motor still dominates the motors. But in industrial and residential applications, odds are that it's the AC motor that dominates. These are some of the devices we looked at that produces AC. This is very important. This is the symbol for an AC voltage source. We talked about the repetition and gave out some terms, show how AC is actually generated on a circle, which is very, very interesting. And if we spin this thing through a magnetic field, of course, it generates a waveform that we refer to as a sine wave. And we talked about a cycle. We talked about different things. Talked about a cycle, talked about an alternation. These are some, of course, some definitions that you really need to understand. Also, we talked about the sine, why it got the name, because any amplitude relative to 0 volts would create a triangle, and we use the sine to solve for what we call the instantaneous voltage of the AC sine wave. So that's why it's became known as a sine wave. This gives a really, really good example of the rotation. Of course, we know now, you can actually see this obviously, that 50% of the amplitude is actually occurring at 30 degrees. 45 degrees is actually 70.7% of the maximum amplitude, which we call VP. This is what we showed. Came up with the different ops. It talks a little bit about trig, not very much, and then we came up and figured out how we would solve for the opposite, which would be what we call the instantaneous voltage. And this to do the hypotenuse times the sine of the angle. We looked at what V average is. This is kind of misleading in the textbook. It's not the average, it's the average of an alternation. And of course, the formula that's easier for me to remember is 2V peak over pi, or 2 over pi times the V peak, which is easier for me to remember. And of course, this is where the 0.637 came from, that if you take 2 and divide it by pi, which we use 3.14, then this is where this number comes up and gets to. Talked about different types of waveforms, AC waveforms. We call this a triangle wave, we call this a triangle wave, and we refer to this as a sawtooth. These are some of the formulas, and I changed this sign a little bit. Normally, what I like to do, instead of trying to remember when did I use 2.82, when did I use 1.414, when do I use 0.707? I try to remember 0.707, and I'll reiterate this again. I understand that RMS is an effective voltage, and it considers V peak, it configures every angle, and also zero is in the mix. So that means VRMS is always less than V peak, and for some reason, people try to get those reversed. And I think about the peak of a mountain. An RMS will be somewhere down the side of the mountain. Well, the peak of the mountain is always the highest part. So the peak of a sine wave is always the highest part. So if I want to go to RMS, if I can remember this 0.707, then all I have to do is either divide by 0.707 or multiply by 0.707. And of course, I know if I multiply by a fraction, I come up with a smaller number. If I divide by a fraction, I come up with a larger number. So VRMS is always less than V peak. So if I know V peak, then I can calculate VRMS by multiplying it by 0.707. Or I could divide it by 1.414, which is the reciprocal of 0.707. We can change multiplication programs over to division programs just doing what we call the reciprocal of the minuend. I guess that's what they call it. I can't remember. Or the multiplier. I'm sorry. Of course, what happens is it turns a multiplication program into a division program or vice versa. But trying to fool around with when to use 1.414 and when to use 0.707 gets kind of confusing even for me. So what I remember is just 0.707. If I want to go to VRMS, I want to come up with a bigger number. If I'm going from VRMS to V peak, then I'm going to divide by 0.707. Or if I want to go in V peak, to get V peak, if I measure V peak to peak, now why is this important? Because on the oscilloscope, which is the main tool that we use to make measurements in solid state, V peak to peak is just like what it sounds. V peak to peak would be a measurement from the top of the waveform down to the bottom of the waveform. Now this peak right here is a mirror image of that peak right there. So if I measure V peak and it's 5 volts, then this is a negative 5 volts, and the difference between a positive 5 volts and a negative 5 volts is 10 volts. So that means if I was to make a measurements between the positive alternation V peak and the negative alternation V peak, we refer to that as V peak to peak, which is important because that's what the test equipment oscilloscope actually measures. But if I know V peak, I can calculate V peak to peak by just multiplying it by 2. Or I can divide it by 0.5, or I can multiply it by 2.82, which takes into consideration going all the way from VRMS. But now I've got to remember all these numbers. So it's real easy for me to remember that V peak to peak is twice V peak. If I know that, and V peak is 1/2 of V peak to peak, which makes it pretty easy. We went overhead and we talked about a little bit about three-phase power. We looked and saw how three-phase power is generated by three-phase alternator or three-phase generator, AC generator. And three-phase power, we can actually see that if this is 90 and this is 180, then it's going to cross at 45 degrees, which would be 120 electrical degrees between the two. This is an example how three-phase is generated or sent out. This is a formula wheel that I need to run this slide off and give y'all this. You won't be able to use it on a test, but it would help you while you learn these formulas. Ohm's law and Watt's law, these are formulas that you should know. I shouldn't have to tell you that. These are basic laws of electricity. These are our power formulas for single-phase AC, which is what we have in our house. So our house gives us single-phase AC. Single-phase AC is a lot cheaper to deliver than single-phase. Three-phase is a lot more efficient to transmit from place to place. So if you had three-phase in your house, what that means is out there on that power pole, instead of having one transformer to give you single phase, they would have to have 3 of those big old transformers out there to give you 3-phase. And you can understand why they don't want to do it. Those transformers cost a heck of a lot of money. These are our power formulas that you should know. So power is equal to V times I. And so I would equal to P over V. And of course, V is equal to I times R. So this is our main power formula. And what we're trying to do here is understand why it's more efficient to transmit AC. So we'll look at this, we looked at this thing right here. And what we can do with AC is we don't change a transformer doesn't change the power, it changes the voltage. So if the power into the transformer and power out of the transformer is equal, that means if it steps up, there'll be less current required in the secondary than in the primary. So this is some examples we went over real fast that if we deliver 100 watts at 100 watts at 10 amps, it would, if we deliver 100 watts at 10 amps, it would take, if we delivered 100 watts, 10 volts. If we had delivered 100 watts at 10 volts, it would take 10 amps. To deliver 100 watts at 20 volts, it would only take 5 amps. To deliver 100 watts at 100 volts, it would only take 1 amp. To deliver 100 watts at 1,000 volts, it would take 100 milliamps. And to deliver 100 watts at 10,000 volts would take 10 milliamps. So you can see, and we're not talking about changing the voltage on the load. We're talking about changing load voltage while this is being transmitted. Now notice you just can't change the current to the voltage to a device without changing the resistance of the device. So what this means is loads are designed to run under a specific voltage. They're designed. So most of your high current or high wattage devices are designed to run at your house or designed around 240. Your lower current devices your lower wattage devices are designed around 120. Now the advantage of a low voltage is that it's safer. The advantage of high voltage is that it requires less current, which means we're going to be able to use smaller conductors. These are some examples of 3-phase transformers. Now this is what would be required at your house right here if you had 3-phase power to your house. And these transformers are not cheap. These are substations, by the way. Y'all probably heard of these. These are the devices that are going to step the voltage down for safety, and it's going to step it up for transmission. So we looked at this, and it went through several different scenarios of trying to transmit 1,000 watts of power. So you see over our high tension line, it's only requiring 3.6 milliamps. Well, out here, what we're getting into our house at 120 volts would be 8.3 amps. But this device that's needing 1,000 watts would be designed around 120 volts. This is 3-phase power. Normally in a voltage and current. So this is a new slide, so I'm going to read over. Normally the voltage and current in one phase is measured. It's real hard to measure the current in 3 different phases and then calculate that at 120 electric degrees. The power is delivered on 3 phases that are 120 electrical degrees apart. This creates a power that is the vectored sum of the 3 phases. So what it is, it's the sine of 120 degrees or 30 degrees, which is absolute value. So if you took the sine of 120 degrees, it's going to be a minus 1.73. But actually, it's the absolute value. So that the absolute value is a number. It's always considered to be a positive number. Now, what's nice about this is that 1.73, which happens to be the square root of 3. So you know you're dealing with 3-phase. So all you got to do is you can measure the voltage in one of the phases. You can measure the current in any phase. And then you can multiply that by the square root of 3 because that's 3-phase. And this would give you the total power delivered to the load. And what we can do here is we can measure the voltage in one phase and the current in that phase, and we can calculate the total phase in the 3-phase circuit. So if you notice, all the power formulas are exactly the same that you learned in DC, except here we're going to multiply all the answers by the square root of 3 to get the total power in the 3-phase system. We talked about why we use RMS, because we can't use the DC average, if I did the DC average of a sine wave, it would equal to 0. So, but they wanted to come up with a way where we could get an effective voltage where the negative voltage did just as much work as the positive work voltage. And this is where they came up with root mean square, or what we refer to as RMS. If we don't give a value in AC, if we just say 120 volts, then that is RMS. If it's going to be peak or peak-to-peak voltage, we would specify V peak or V peak to peak. Now, on a sine wave, we can always take the peak value and multiply it by 0.707 to get the RMS value. We have what we call true RMS meters, which are very expensive, about as twice as expensive as a standard meter. And a true RMS meter actually calculates RMS. And the problem is that means it's actually a computer that does the actual math. This shows you RMS would create the same amount of heat in a resistor that the equivalent RMS value does, that DC that the RMS value would do. This is some problems we work. We're not going to do this in this slide. We're trying to just go back and review real fast. We talked about the different types of ohms. Ohms is a measure of opposition. What in this class we're going to have to pick up 3 different types of opposition. You learned about resistance in DC in intro. In AC we have 2 more we call reactance and impedance. Well, reactance is the opposition. This actually changes with frequency. So reactance is dynamic. Resistance is static. So I can put a different frequency on a resistor, and it gives, so a 100 ohm resistor will always give me 100 ohms. A device that is reactive, it gives me a resistant different frequency depending on frequency. Now, impedance is a term that we use for circuits that contain both reactive and resistive devices. That is technically what it is. But what you're going to find out, we've almost started to use impedance anytime we talk about an AC circuit, whether it has reactive devices in it or not. And that's just common terminology of the field. Opposition to current flow that don't change. We looked at reactance. Now this is what we stopped at a little bit and show you a device called a capacitor. As frequency goes up, opposition goes down, according to the factors, the formula for what we call capacitive reactance. Now, an inductor, as frequency goes up, inductive reactance goes down, which is very interesting. So this is pretty interesting. What happens is that inductors and capacitors actually, if we put conductors and capacitors in the same circuit, they cancel each other out. So, which is really, really neat. So, if I had an inductor that had the same capacitive inductive reactance as the capacitor had capacitive reactance, those devices would physically or electrically cancel each other out. These are some pictures of some capacitors. Now, we're going to talk about this a little bit just so we understand. What happens when we have inductors or capacitors, they do something that you'll really learn in AC. They create what we call a phase shift between the current and the voltage in a circuit. Inductors causes the current to lag behind the voltage, and capacitors cause the current to lead the voltage. Now, what happens is that this phase shift is required by single phase motors. We can't make a motor rotate unless we have a field that is moving in reference to another field. So AC motors are going to have a winding they call a start winding, and they're either going to use an inductor or they're going to use a capacitor to cause a phase shift in the start winding to cause the single phase motor to spin. So these are very, very important. And by the way, if the capacitor goes out, the motor will sit there and hum. It can't start up because it don't see a phase shift. 3 phases creates a rotating magnetic field. So this is one big advantage of a 3-phase motor over a single-phase motor. Single-phase motors are going to have a start winding which has inductance in it or has capacitance which creates the phase shift. Inductive motors they're referred to as split-phase motors, and these are for low starting torque applications like for fans. Capacitive motors have a lot better starting torque because they can create a greater phase shift. And what this means is most of your motors that are actually run something like compressors or stuff like that. These are going to be capacitive motors or capacitive start motors. This is actually a picture using an oscilloscope, and this is something a meter will never show you. And what I've got is I've got a meter in I got a scope in 2 different places in the circuit, and it literally actually shows the phase shift between the 2 places in the circuit. What AC does is it creates a out of phase power. Now what that means is if I measure current and voltage in an AC circuit, it's going to give me a untrue reading. It's going to say, okay, it appears you have more power in the circuit than actually the work that you're getting. So this is why power in an AC circuit is not called watts, it is called volt amperes. Now, Alabama Power charges you for watts because they compensate for the out of phase power. So it's compensated for you. In a big plant, they have to compensate or try to get rid of volt amperes. Now, what we do is calculate something called the power factor, which is the ratio between the true power and the apparent power. And so this is the formula. So we take the true power, which was the power delivered by R. We take the apparent power, which is the power delivered by true impedance, and then we divide those out, and this comes up and gives us a power factor. The ultimate goal, of course, is for the true power and the apparent power to equal each other, which means that if the true power and the power factor equals, we have a power factor of 1, or what we call 100%, which is real good. Normally, the power factor is going to be less than 1. Alabama Power requires a power factor on these big industries of around 95%. Why? Because all your transformers and all your generators and all your conductors and everything in the power grid has to deliver apparent power. So it's a lot cheaper for them to require a real high power factor than it is for them to put those transformers out there and redo all their transformers and all their conductors to handle apparent power. So, and if you're a big corporation, you have to come up with a way to get this true power better, this power factor of around 1. Okay, conductor terminology, we looked at traces and conductors and cables, talked about that, looked at what a trace looks like, and a lot of y'all picked up a printed circuit board. We looked at what conductors are equal to, or what some people call them wires. We looked at a cable, which are individual conductors that are in a common jacket. We have flat cables and we have round cables. We talked the difference about stranded wire and solid conductors. Stranded wires are easier to route, they're easier to bend, but they're more expensive per gauge. Solid strand wires are easier to terminate. We can wrap them around screws and tighten them down. These guys here, if we put them under screws, they're going to spread out, which we refer to as bird caging. Normally these, we have to put them in some type of compression terminal, or we have to put them in what we call a crimp terminal, or we have to solder them. We can solder this and make them appear kind of like a solid strand wire. Termination is the act of bringing conductors to an end. Splicing is when we permanently or semi-permanently join 2 conductors together. Multimeters are very, very important. We need to understand the difference between making measurements with a voltmeter, an ammeter, and a ohm meter. So undoubtedly, for some reason, I didn't put ammeter in this list. So I'll make that correction right now. So what we do with an ammeter is, an ammeter, what do we do? We got it next. I think the next slide will probably clarify this. So these are the way we connect our meters. So what we do is that for safety, for voltage measurements, if possible, remove power from the circuit when attaching or disconnecting leads. Use alligator clips to attach meter leads. Select the correct unit, AC or DC, being tested on your meter. On manual ranging meter, select the correct range within the correct unit. Now, when we talk about place the black lead on the meters on common and the red lead in the plus terminal. Okay, we're talking about the leads, meter leads. Place the leads across in parallel with the device or power source to be measured. Voltage measurements in DC requires the black lead to be positioned toward the negative terminal of the source. Now, when we say requires, this is kind of misleading. It don't require it. In the old analog meters, which means they only deflected in one direction, if you got your black lead and minus lead messed up, then the meter would reflect backwards and hit what we call an end stop, and it could be in your pointer. Digital meters don't care. What would happen would be if you put the black lead toward the positive voltage terminal, the voltage source, and you put the red lead toward the negative of the DC voltage source, it would measure a negative voltage. It would be the same as you measured positive, it would just get the polarity wrong. Now, seriously, if you're measuring AC, it does not matter, because technically AC does not have a polarity. So that means whether you use the black lead or the red lead as the common, it makes no difference on AC. Because it is not a common of a circuit, it's the common of the meter, which means it's the reference for the meter. The meter is totally isolated from ground. It's totally isolated from the circuit until you push that common into the circuit. Then that becomes the common of the meter. It does not come the common of the circuit. If you turn the power off, of course, you got to apply power. You're going to return the power, if possible, remove power, and disconnect the probes. So this is showing you how we would measure voltage. Okay. Current measurements. Now this is using a current meter, not what we call a clamp-on amp meter. A clamp-on amp meter technically does not measure current. What the clamp-on amp meter does, it measures the strength of the magnetic field being produced by the AC current flowing in the circuit. Now, the magnetic field is proportional to the current flow. So you're not actually measuring current. The meter is measuring the strength of the magnetic field and interpreted on the display as a current. Okay, we got to put, on the meter, we put the black meter lead in the common terminal of the meter. We put the red lead in the amp meter reading of the terminal. Now, normally on some ammeters, you have multiple terminals. You have one specifically for milliamps, and you have the other for amps. So most of your digital multimeters, not clamp-on amp meters, usually have two individual terminals. What we normally do, if we don't know what the current is, but we know it's less than what the meter range is, we put it on the amp. We put it in the amp setting, make a measurements, and if it gives me less than less than 1 volt, then we would turn the meter off. We would turn the circuit off, we'd turn the circuit off. We would pull out the red lead and move it over to the microamp or the milliamp terminal. We need to select either AC or DC amps. If it's manual ranging, with power removed from the circuit, break the circuit. So you literally got to open the circuit, and you got to place the meter leads in series with the load. Record the leading, remove power, then remove the leads and reconnect the circuit. So this is how a true ammeter. So you got to make the current flow through the meter. Now what you got to understand, since it flows to the meter has almost 0 ohms of resistance between the common and the amp scale. So that means if you put this sucker across anything, you are going to create a short or a short circuit, which is very dangerous. So this is why your meters, your amp scales are fused. And don't ever put a bigger fuse size in there, and don't ever override that fuse. Now on meter, what we do is we put the meter leads into the meter exactly the same way, and then we remove power. Remove power is the first thing. Place the meter leads across the device to be measured, record the reading, and then remove the meter. Always make sure you remove the meter. If you turn power on, you could definitely damage your meter. You might even damage the circuit. Okay, so this is the way we measure resistance. Now we notice here that the power is turned off. Okay, the power is turned off. So if you got a DC system where the power is not, it doesn't have an on-off switch on it, then what you're going to have to do is you're going to have to remove one of the battery leads. This is different types of meters we're going to show you. This is an auto ranging digital multimeter. This is about whatever. Now, what you're looking for a meter, and we'll look at more as we go along, for electronics, you're looking for a meter that can measure AC and DC millivolts and AC and DC milliamps. You're also looking for a meter that is considered what we call a category 2, category 3 meter, and we'll look at that in a minute. This is an analog meter that are still available. We use analog now. What's nice about analog is that if you got a slow moving signal, the dial will actually move back and forth. So these are still used widely in communications, where we have to set up what we call tune circuits. So anybody that tells you that analog meters are no longer used, they have no idea what you're talking about. It's just I still have an analog meter at my house, and I still have to use it every once in a while. Now, the next thing we're going to talk about is a clamp-on meter. Voltage and resistance measurements are made in the same multimeter. Current, most clamp-on meters will only measure AC current. Meter that measures AC/DC currents are available, but they cost a lot of money. AC we can do with a current transformer. DC we have to use an electronic device called a Hall effect sensor. So it is literally electronics measuring the DC current magnetic field. So this is why clamp-on ammeters that have the ability to measure DC currents with the clamp. So I'm going to currents with the clamp. Now they can measure DC current like a standard meter through the terminals on front of this. A clamp-on meter, though, you don't use the leads. All you do is take that clamp, you put it around the circuit, it picks up the magnetic field and gives you the strength of the field and gives you a reading. If you're going to use the measured DC, a low current DC, then you're going to have to use a regular meter. So I don't know if this is a picture of a clamp-on ammeter. So what we do is we push down on this little lever right here that opens up the clamp. You put a single wire, never put more than one wire through this, and then you make your measurement. Okay. If you're using a clamp on, you need to make sure you remove your leads. For one reason, you don't want these things flopping around. So just remove the leads. Now we can't see, but down here somewhere we have an amp scale, and that way what we'll do is we can use this to measure low current DC. Then we use this to measure AC, high current ACs. Now what you'll find usually on these clamp-on meters, the clamp current, minimum current is around 40 amps. So these are sure enough high current devices. Now what you need one of these for, if you're in the electrical trade, not the electronic trade, this is the meter you need to get. So you need to buy a nice clamp-on ammeter, not necessarily true RMS. Just normally true RMS is only required for signals that are not, for AC signals that are not sine waves. These are produced by variable speed AC drives. They're produced by pulse width modulation drives. So if you're measuring inside those situations, then what you would want to do, you would want to use a true RMS meter. If you're just doing everything is 60 cycle, everything is a sine wave, which is true in the electrical trade, then buying a true RMS meter, you're literally wasting your money. Okay, so that's one I recommend. Now you'll have problems in AC and DC. But what we'll do in those classes, we don't want you to buy 2 meters because these meters are not expensive. What you'll do in DC is we'll furnish the meter. When you get into AC, you're going to be required to have a meter in AC. You're going to be required to have a meter in motor controls. You're going to be required to have a meter in solid state. So what we recommend on those is if you're in the electrical trade, you won't be taking solid state. But if you're in the electrical trade, when you're taking AC, go ahead and get a clamp on amp meter, and we'll let you use one of our bench meters to measure low current and low voltage AC. And then that way you won't have to go out and buy 2 meters. If you're in electronics, don't buy one of these. These won't serve you well in electronics. So what you want to do is make sure you get one of these auto ranging or manual ranging meters. We specify it's got to be at least a category 3 meter for motor controls, and it's got to have the ability to measure millivolts and millivolts AC and DC, and milliamps AC and DC. Okay. What we'll look at now, this was added lately. This might not be on the PowerPoints up on the internet, up in Blackboard, so I'll do this. What you look at when you now it's required by a safety standard called NAFTA, put out by the National Fire Protection Association, called the 70E. Now, y'all probably heard about National Electrical Code. That's NEC. National Electrical Code was actually put out by NAFTA, the National Fire Protection Association, or a 70 committee. What NEC covers is the safe installation of equipment and wiring. Now, if you hook up everything safely, normally that means you should be safe. Okay. But over time, they realize that we do things that cause unsafe practices. And one of the things that NEC does not specify is transient voltages that get on these power lines. So transient voltages can get on these lines by a big plant like U.S. Steel. All of a sudden something happens and the power goes off. Kills at the whole plant. Well, that's going to create and the regulators way back at the plant that it comes from don't see that way down the line. And what this will cause a voltage spike. So big old loads, or if a tree branch drops across a power line and causes them to touch and then it bounces back up, this causes voltage spikes to move down the line. If lightning strikes a power line, which it does all the time, this causes voltage spikes to fly down the line. Then you're in a high energy circuit, and that voltage spike comes in and jumps across your meter leads and creates an electronic arc, which creates ozone, which creates short circuits, and the meter blows up and the power source blows up and creates what we call an arc blast, which is not fun. So what they did is they decided to come out with a specification or a list of procedures to follow, for companies to follow, to keep their employees safe. So this doesn't deal with you at your house. This deals with the employer and employee safety. And it covers safety for arc flash, arc blast, and it also covers electrical shock. So what they did is they came out with 4 categories of meters. They came out with what they call a Cat 1 meter. Now, Cat 1 meter, these meters can be used to troubleshoot and work on electronic equipment with low voltage supplies. Okay, so that means in DC, in AC, in solid state, in digital, you could use a Cat 1 meter because all these are electronic devices you work on. If you're going to work on single phase AC power, then you're going to need at least a Cat 2 meter. Now, what you have to understand, these meters are downwardly compatible. So that means if I've got a Cat 2 meter, then we can use it as a Cat 1 meter, but I can't use a Cat 1 meter in a Cat 2 application safely. Now, it would probably work, but what we're talking about is getting rid of these voltage spikes, the things that come down the line. Now, we're not going to get in a lot of stuff, but normally these things are rated at 2 different voltages. And this gets people confused, is that you might have a Cat 1000 volt meter, and you think it will be better than a Cat 2 600 volt meter. That is not true. Cat 2 meters can handle the 600 volts at a higher energy level. A Cat 1 meter can't do that. So that means if you got into this and you got a 600 volt high energy spike on a single phase application, it would flat blow up a Cat 1 meter, a 1000 volt Cat 1 meter. Now, when we talk about the rating, the 600 volt rating, that is not the maximum rating of the meter or the range of the meter. This is the amount of voltage spikes it can handle without blowing up on you or creating a short circuit above the maximum rating. So that means if I've got a 1000 volt DC range on my meter and I have a Cat 2 1000 volt meter, then it can handle it can measure a 1000 volt spike on a single phase system. But a Cat 2 meter could not handle a 1000 volt spike on a 3-phase system, if that makes sense. So mainly a Cat 3 meter, which is what we require here, because most of y'all are gonna, if you're in electrical, you're gonna be dealing with 3-phase. You're gonna be doing pulling wire. You're gonna be dealing with 3-phase, but it's gonna be on between the distribution or the disconnect and the power, the actual down drop or the actual source of the power, I guess I'd say. So a Cat 3 meter is rated for 3-phase use, but it will handle 1-phase. It'll handle single phase, and it'll also handle electronics. So what we're saying is, if I had a Cat 1 meter, it would be unsafe on 3-phase. If I had a Cat 2 meter, it might work, but it would be unsafe on 3-phase. If I had a Cat 3 meter, then it would work all the way down the line. If I'm going to get on the distribution side of the system, then I'm going to have a Cat 4 meter. Now, that's not only true, it also says right here. So this Cat 2 meter, don't say that on the Cat 3, the Cat 2 meter can't be used within 30 feet of a Cat 3 source. So that means if I'm over there in a room that's over there by the down drop where my watt meter's at, I cannot use a Cat 2 meter safely because we're real close to a Cat 3 source. And that means it's not going to, the internals of your house is not going to dissipate the heat. Or if we're going to be within 60 feet of a Cat 4 source, we can't use a Cat 2 meter. So we can use it on single phase, but if it's close to a distribution, we're not supposed to use a Cat 2 meter. A Cat 3 meter is on this side, and it does not specify how close you are to a Cat 4 source. Does that make sense? I hope so. Now a Cat 4 meter, it's on the distribution side. Okay, so a Cat 4 meter, anything you work with over here has got to be at least a Cat 4. Now you got to remember, if you get up in here, so we're not talking about the power distribution on the other side. We're talking about after it comes through the transformer. Okay, now you got to remember, you've got to have a meter. Having a meter that's a Cat 4 meter and rated at 1000 volts AC, you cannot get the Cat 4 meter into a 2300 volt circuit. So you got to understand what you're measuring and make sure you have the right category meter plus the range of the voltage that you're going to get into. By the way, if you don't know the voltage you're getting into, don't put your meter in the circuit until you find out. And that's just safety. Okay. This is showing the way we'd use a clamp on that meter. I really should move this up, I guess. So if we got a AC clamp on meter, then we can, this don't show it. You can buy, by the way, most of your more expensive meters like Flukes, which are basically the top of the line meters. Flukes, you can buy a clamp on amp probe, which is pretty neat. Now, if you have one that has the ability to measure AC DC, then of course these are going to be more expensive. This is the clamp on amp meters we normally buy for the electrical trade. And of course these guys, you can get them to measure They usually don't measure DC. They usually measure AC. If you go one that measures DC, it's going to use an electronic circuit called a Hall effect sensor, and it's a lot more expensive. So guys, I think that went back and made up for the loss of that one section that would not overload. I'll go ahead and upload this and paste it. This is the AC introduction part 2. The AC introduction part 1 loaded okay. So I'll get this up sometime this weekend. All right. Hope you have a blessed day. See y'all in class.